Let's take a look at an example problem from Module 12 for Dynamics course. So in this problem here, we can see we have a rod attached over here at some point, pivot point here, O. The length of the rod is given to us as 3 meters. We can see there's an omega of 5 radians per second. And we have a moment up here of 60 Newton meters. And we can see it's rotating here clockwise. So that's all just from the given diagram. In the problem statement, they also tell us the rod has a mass of 20 kilograms, and it's rotating at 5 radians per second. That corresponds with our omega up there at the instant shown. And they also tell us we have that moment there of our 60 Newton meters that we can see right up there, and that's going to be applied to the rod. Now, what are they asking us to solve for? So they want us to find first our angular acceleration, our alpha term here, and the reaction at pin O when the rod is at the horizontal position that we see in the diagram above. So what we want to do now is come up with a plan of attack here. So since the mass center G moves in the radius, the circular radius, so we can see if that's the center of mass there, it's going to move as it rotates in a circular radius here. Its acceleration is going to have a normal component towards O and a tangential component acting downward and perpendicular to our radius R sub G. So now that we've had the opportunity to read through our problem statement and take a look at the given information in our diagram, the next step in our solution here is to create our setup page. So to create our setup page, what I've done is I've redrawn out a simplified version of my given diagram over here. And again, I've chosen to do this in PowerPoint here just to make it easier for you guys to follow along. Nice clear diagrams, nice crisp clean lines, and not my messy handwriting for this one here. So what I have here is I've drawn out my pivot here. Here's my pivot point at O. Here is my moment rotating clockwise here, 60 Newton meters. And here is my omega term here of 5 radians per second. And I know my total length of the rod is 3 meters. So I write this off to the side over my given section over here. There's my omega term. There's my moment there. And they also tell me in the problem statement my mass of the rod is given to me as 20 kilograms. So what are they asking me to solve for? Well, I need to find the angular acceleration, my alpha term here. And I need to find the reaction at pin O when the rod is at the horizontal position that we're seeing up here in our initial diagram there. So I'm going to follow the same procedure for analysis that we just talked about on the previous slide there. So again, that means we're going to need to find our center of mass there and do a couple of assumptions that this is going to be moving in a radius. So one of the great things about doing out our solutions to problems in a program like PowerPoint or LaTeX or Word or any of those things is that we can copy and paste our diagrams, and they're a great reference for us. So I can put that on every page I need to reference it. And this is going to be very helpful for this problem here, where I need to use our free body diagram and reference back to that initial given diagram. So up top here, I have my initial diagram that I've drawn out in a simplistic form. You can see I have my moment here, my length of the rod, my omega term here, my pivot point about O, and that's going to be very helpful to have that right there so I can look quickly at that as I reference down and do my free body diagram out. So that's the first thing I want to do in my solution here is draw my free body diagram. And from there, I'm going to look at just one of the directions. Well, let's just deal with the free body diagram first. So in our free body diagram right here, I take a look at my given diagram above and I say, okay, I'm just going to concentrate on the rod, not going to worry about the weight of the pivot. I'm just looking at my rod itself. What is acting on the rod? What forces do we have? What's going on? So I can quickly reference up here, okay, I've got reactionary forces right here at this pivot point. I've got this moment here, and I'm also going to have a center of mass located at the middle of this rod here for my weight force. And I know this whole thing is rotating clockwise. So all that information is going to help me as I start doing out my free body and my kinetic diagrams here. So for my free body diagram, again, I have these reactionary forces at point O, my pivot point. So I'm going to deal with an NT coordinate system here. So in the NT coordinate system here, I have my T, O sub T, acting in my tangential components, and N acting in my normal component here at my point O here. So for this here, I also see what other forces I have external acting on it. Well, I've got this moment here, my 60 Newton meters, going clockwise. And then I also have my weight force over here, which is mass times the acceleration of gravity, where mass is given to me as 20 kilograms. My acceleration of gravity is 9.8 meters per second squared. So I can plug that in there and put it right at my center of mass here, G. So this is a simple 3-meter rod. Center of mass of a simple uniform rod is half of it. So right there, halfway up is 1.5 meters away from our pivot point and 1.5 meters away from the end of the rod right there. So now that I have this free body diagram in front of me, I can take a look at it and start coming out with my equation of motion. So recall Newton's second law, force is equal to mass times acceleration, and I can start plugging in there. Okay, summation of forces, that's what I'm going to pull from my free body diagram. Now on the right-hand side of this, I have the second half of Newton's second law, mass times acceleration. Now I'm dealing with my normal component, so I have my a sub n, my normal component of acceleration. Well, I don't have much information by problem from that, but I do have this information over here. So I can recall for the normal and tangential components of my acceleration equations, I have these relationships. So let's just look at the normal. Our a sub n, our normal component of our acceleration, is equal to r omega squared, where I have my r, my 1.5 meters, and I have my omega given to me as 5 radians per second in the problem statement, so I can plug those in right here. So my a sub n is now r sub g omega, where g is 1.5 meters, so there's my r sub g right there. So now that I have the right-hand side of that, and I know I have known values I can plug in there, and I've dealt with this a sub n, let's look at the left-hand side. So summation of forces in my n direction. Well, if this is my n direction here, I only have one force. I have my O sub n. So my O sub n is equal to my mass, 20 kilograms, times r sub g times omega, so 1.5 times 5 squared. So from that equation there, for my equation of motion, so summation of forces here in my n direction, I can see that my O sub n is equal to 750 newtons. Now the next thing that I want to do, now that I've dealt with summation of forces in my normal direction, I want to deal with summation of forces in my tangential direction. So in my tangential direction here, I have, looking back at my free body diagram, I have, okay, that's going in the tangential direction, and this is going in the tangential direction here, and they're going opposite, so they should have opposite signs, depending on what I've defined as positive and negative. So if I consider the positive to be going down with my weight force and negative to be going up, make sure my sign convention matches that. So I go back to Newton's second law for my equations of motion. Summation of forces equal to mass times acceleration. In this case, now my acceleration is a sub t, tangential component of acceleration. So I come back over here now and recall that the normal and tangential components of acceleration equation. So a sub t is equal to my alpha times my r sub g, so I can plug that in right there. Then I can see that that comes back over here now. There's my a sub t replaced by my alpha times my r sub g right there. So I now have the right-hand side, and I know I have my mass. I know I have my r sub g again. And the only thing that I don't have is my alpha term. So that'll be the thing that I'm going to need to solve for. So now I can deal with the left-hand side of my equation over here, summation of forces in my tangential direction. So I come back to over here, okay, I have my O sub t, I have my g. So my O sub t is going to be in the negative direction if positive is going down. And I have my weight force here, which is mass times acceleration due to gravity. So my mass is 20 kilograms. My acceleration due to gravity is 9.8 meters per second. This is equal to the right-hand side of my equation, which my mass is 20 kilograms. My r sub g is 1.5, and my unknown here is this alpha term. So I'm going to need another equation now because I have one equation and two unknowns. I don't know my O sub t and I don't know my alpha. So that's where we're going to go and come up with our third equation. So where this third equation comes from is from our summation of moments about our point O here. So about this fixed pivot point here, we're going to sum all our moments. Now we can see from our given diagram, we have this external moment here given to us as 60 Newton meters. We also have our weight force times its distance of 1.5 meters from the center of mass there. They're all creating a moment here about O. So if we sum the moments about O, that will give us our third equation. So what we want to do now is take a look at our kinetic diagram down here. So here's our kinetic diagram. And what we want to do is we want to break the acceleration down here, the right-hand side of Newton's law, mass times acceleration, down in terms of its normal and tangential components. So if we look at this here, for n direction here, we have m times a sub g n. So our n component right here is going to have this form here, m omega squared r sub g, when we plug in for our a sub g in the normal direction. So we see that there. Now we have our m omega squared r sub g acting in our normal direction there. Now we want to do the same thing for our tangential component of our mass times acceleration, second half of Newton's law here in our kinetic diagram. We see here is our tangential component here going down here with our weight force or our gravity force right there. So we can see that this one here is in the form of mass times acceleration due to gravity, a sub g, times t, and our tangential component over there is equal to, when we plug in there for our a sub t, we have mass times our alpha times r sub g, so that's where we have our mass times our alpha r sub g there. So this is going to form our kinetic, the right-hand side of our summation of moments here from our kinetic diagram. Now, the thing that we want to note here, if we reference back to this general form on equation 715 in our textbook here, that the moment of a sub g in our normal direction is not going to be included here. And this is because the line of action of this vector passes through O. So we can see the line of action of this vector right here is going to pass through O. So we're not going to deal with our m sub ag in the normal direction. So now we have this general form here. Summation of moments about O is equal to, the right-hand side of this here is R sub G times M times our A sub G in the tangential direction there, plus our I sub G alpha. Well, our A sub G in the tangential direction there, we can now replace this A sub G here with our R sub G alpha right there, and we can plug that into that relationship there. Which brings us to our third equation over here. Once we plug in there, summation of moments about O is equal to our I sub G alpha. I'm going to pull this one out front here, times this relationship here now when we plugged in for our R sub G term over there. So now that we have this relationship here, the next thing to ask ourselves is, okay, what else can we plug in here? Well, we can plug in for our R sub G term, and we can plug in for our I sub G term. So for this shape here, we can look up our I sub G here. I sub G is going to be equal to ML squared over 12, and our R sub G here is going to be 0.5 times the total length right there. So we can plug that in, rearrange now, plug those relationships back in for my I sub G right there, and my R sub G in those two spots right there. I do that now, and I say summation of moments is equal to, and I realize I can pull out this alpha term right here to get it in this general form there. Make life a little bit easier. So now I just have my I sub G times my M times R sub G squared term there, because that, you can see, is multiplied in two spots there, R sub G. So when I plug that in there, what I end up with down here is pulling out my alpha here is equal to now my I sub G times the alpha term here is equal to ML squared over 12. Then we have over here now my 0.5 or my ML squared now when I square this term here for both the R sub G's over my 4 there. Find a common denominator of these guys. I can rearrange this, and what I end up with, summation of moments about O is equal to ML squared over 3 times my alpha term. So this now leads us that we have our I sub O is equal to that right from above there, our ML squared over 3 times our alpha. So now if we continue on with our summation of moments here, what we can see is from equation 3 right here, we found this solution. So the summation of moments about O is equal to our alpha times our ML squared over 12 plus ML squared over 4, which we found we could reduce down to ML squared over 3 times our alpha there. So now we have this relationship here that the summation of moments about O is equal to ML squared over 3 times our alpha term. So our next step here is to take a look back at our free body diagram and say, okay, what are our moments about O? Let's deal with the left-hand side of the equation. Now that we've already simplified the right hand down from our kinetic diagram, we'll deal with the left side from our free body diagram. So we have our point O here. We have our normal and tangential components of O, which are reactionary force, which aren't going to cause any moments about O, which is why we chose to sum our moments about O rather than G. And our only moments are going to be coming from our external moment here given to us is 60 Newton meters, and our weight force times this distance here of 1.5 meters. These are both going to be rotating clockwise. We're going to consider that to be a positive moment when we're going clockwise for our coordinate system. So with that there, what we can do is say, okay, our 60 Newton meters is going to be part of our summation of moments there. Plus now we have our weight force, which is mass, 20 kilograms, times our acceleration due to gravity, 9.81 meters per second squared, times that distance there. And you can see I've done out my units for unit analysis here just to double check. Now this is equal to our right-hand side of the equation. Now I can see here I've got a mass that I know. I'm going to pull that out front here, and I put my mass right there of 20 kilograms, times my L squared. Well, my L, the total length of this is 3 squared, divided by 3 times my alpha. So that's my right-hand side of the equation here. I can reduce this down and simplify a little bit here and solve this now. My only unknown, if I look at this whole equation here, the only thing I don't know here is my alpha term. So I can plug all this in, reduce it down. What I end up with here when I do this out is 20 times my 9, 3 squared over 3 is 3. So 20 times 3 gives me 60 alpha on my right-hand side. I do my math, simplify down on my left-hand side, and end up with 354.3 Newton meters when I do out my unit analysis is equal to my 60 alpha. So I can rearrange this and solve for my alpha, still doing out my unit analysis here to make sure I'm in the right units. So my alpha is equal to 354 divided by 60. Do my unit analysis out here. What I end up with is alpha is equal to 5.9 radians per second squared. So with this alpha term here, I can plug this back into equation 2. So I refresh my memory. This is my equation 2. Summation of forces in my tangential direction is equal to m times the acceleration tangential component, which I plugged into an r sub g times alpha for my tangential component. So that led me to, when I did out my free body diagram, my equations of motion here, my negative O sub t plus 20 times 9.81, my mass times acceleration due to gravity for my weight force is equal to my right-hand side, my mass here, times that distance of 1.5 times my alpha, where I had two unknowns and one equation. Well, now I have an alpha term that I can plug in there, which gives me one equation and one unknown. So I rewrite that equation down here. Negative OT plus my 20 kilograms times 9.8 meters per second squared is equal to my mass here of 20 kilograms times my 1.5 meters times my alpha. I'll plug in now for my alpha here of 5.9 radians per second. Plug that all in there. I can reduce and simplify. So my negative OT plus 196.2, when I do my math out here in newtons, is equal to 177 newtons. And again, my unit analysis makes me have newtons on both sides. That's great. So my O sub t, when I do that out there and solve for it, O sub t is equal to 19.2 newtons.